Story time. When I was in high school taking geometry, we had to learn how to do proofs. And it's really not a how to do proofs, but develop an understanding of proofs. So we would prove things like what we're about to prove. So prove that the opposite angles of a parallelogram are congruent. Well, you can look at it and tell they're congruent, right? I mean, it's kind of common sense. So I went to my teacher and I said, Ms. Brewer, this is really common sense. Why do we have to prove something that's common sense? And I didn't understand her answer at the time, but now I've gained an understanding of it and a respect for it. We are developing the ways we think so we don't make assumptions. So in the future, we will be able to prove things that are not so obvious. So even though I can look at this right now and say, okay, let's just go ahead and start by labeling this thing ABCD, that the measure of angle A is equal to the measure of angle C because it looks like it. And you can look at that and say, yeah, whatever. Do you know it? Well, textbook says so. Well, how do they know it? How do they know? Like, let's prove this. Let's make some logical arguments. There's a book, I don't have it on me, it's actually at my house, Nerd Tactics. It's called Euclid's Elements. And the idea of mathematical proof really was developed in ancient Greece with this book. It's a multi-volume series, and the one I have is condensed. Flexing my math stuff. Yeah, all mine's condensed into one volume. But it is a way that mathematics really took off in terms of, okay, I know this because I know this, because I know this, because of this, mathematics developed from, let's just count, to we can make logical arguments about things, prove other things, and continue to build on the knowledge. And mathematics continues. We continue to discover new things about mathematics that we didn't know because we're building on previous knowledge, things that are not obvious, that we are learning by developing the things that are obvious and developing our thinking about those things. Okay, enough of a sales pitch on why proofs are important. Let's just jump into it. We have A, B, C, D. I recommend you label yours like I've labeled mine, and we're going to prove that the opposite angles of a parallelogram are congruent. I'm going to just end this thing by saying, okay, angle A is congruent to angle C, angle B is congruent to angle D, and then we're just going to go home and we'll be fine with it. But we have to get there first. So before you go home, let's actually start with what's been given. I'm going to start by saying, okay, well, I've been given a parallelogram. What do I know about a parallelogram? Other than the properties that I've already just assumed were true, well, I know that the definition of a parallelogram, the opposite sides are parallel. So I'm going to say that AB is parallel to CD, and that means that this side is parallel to that side. And we'll also say BC and AD are parallel. We'll do that in the same step. So please don't think about this as, oh, what comes next and what's the next step? Logical thinking, that's the next step. It's not always going to be the exact same thing. But BC is parallel to AD. Now, with every one of these steps, I'm going to say, well, how do I know that? Well, I know this because I was given a parallelogram. So this is the definition of a parallelogram. There's a symbol for parallelogram, and it's a parallelogram. Alrighty, so what I'm going to do is jump to the next step and say, okay, well, I want to prove that these angles are congruent to one another. And yeah, these opposite angles are congruent to one another. So what do I know? Oh, well, given parallel lines, I know a few things. If I know parallel lines, then I have, let's see, two parallel lines and a transversal. So I could say that angle A plus angle B, measure of angle A plus measure of angle B, let's be specific, is equal to 180 degrees. And I know that because same side interior are supplementary. Now, while we're at it, why don't we just go ahead and say that B and C are going to add up to be 180 degrees as well. So the measure of angle B plus the measure of angle C is 180. Now, this is going to seem like a lot of writing, but by the time we're done, when we get to the very bottom, we're going to say the measure of angle A equals the measure of angle C, the measure of angle B equals the measure of angle D, right? So that will prove what we have said, and therefore I'm going to need to continue to list all the stuff. So B plus C is 180, C plus D is 180, so the measure of angle C plus the measure of angle D equals 180 degrees. And the measure of angle D plus the measure of angle A equals 180 degrees. And for each one of these, I'm going to list how I know it. Well, how do I know that? Well, glad you asked. Same side interior angles are supplementary. There we go. Okay, good to know. So we could call this step 1 if you wanted to. We could call this step 2, and we're going to continue till we get to the end. So I want to show that, let's just take a couple angles. I want to show that A is congruent to C. If I want to show that angle A and angle C are equal in measure, then what I could do is just look at things that involve A and C. Let's just take the first two right here. We're going to say, let's see, if this equals 180 and this equals 180, A plus B is 180, B plus C is 180, and they must equal each other. So here goes, step 3. Measure of angle A plus the measure of angle B equals 180. Don't put 180. We're going to put measure of angle B plus measure of angle C. B plus measure of angle C. Right? How do you know that? Well, they both equal 180. There's a name for that. That's called the transitive property of equality, he said with very bad handwriting as the TV was shaking. It felt like it jolted a little bit earlier, and it was like, and I thought, oh, it's not going to fall. That's why I awkwardly looked behind it, in case you're like, what was that about like 4 minutes ago? I was looking behind it to make sure it wasn't coming off the wall, because it almost did one time. All right, they fixed it much stronger. Now, knowing where we're going, I want to say that A is equal to C. I also want to say B equals D, so we may have to make another equation. Let's do the same thing with the bottom two. Do I have to use the bottom two? There's probably another way around it, but let's not. Is there another way around it? B and D? A and C. Oh, it's not going to be the bottom two. It's going to be C, D. Now let's use these two right here. Yeah, BC. No. We're going to use, see, sometimes when you're doing a proof, you have to think through things. By the way, I'm thinking ahead a little bit. In just a minute, I'm going to say, well, let's just subtract the measure of angle B and A equals C, right? Okay. I want to be able to also say B equals D. So I need a B and I need a D. Oh, here we go. First and last one. They both have an A, and I could subtract that. So we're going to say the measure of angle A plus the measure of angle B equals 180, which is also the measure of angle D plus the measure of angle A. And again, same thing, transitive property. Let me take that out, not the whole thing. Let me just erase that little doodad right there. And we're going to say that this whole thing is because of the transitive property. So we have two equations. And normally we would just deal with one at a time. But by the time I'm done, I want to say these two are equal, these two are equal. So just looking at the first equation, step 4, I would subtract the measure of angle B from both sides. And that would say that the measure of angle A is equal to the measure of angle C. Okay, how do you know that? I subtracted, right? That's the subtraction property of equality. So subtraction, handwriting's getting terrible, property, I'll blame the TV, of equality. Feel free to put the equal sign there. I could have done the same thing right here. And it's the same, okay. A plus B equals D plus A. Well, if you subtract the measure of angle A, then you're going to have the measure of angle B equal to the measure of angle D, because of the subtraction property of equality. Therefore, opposite angles of a parallelogram are congruent. Now, in a lot of very formal mathematics, you would get to the end and you would say, therefore, opposite angles of a parallelogram are congruent. I'm running out of space, so I'm going to put it, but I'm not going to put it at the bottom. I'm going to bring it over here. And therefore, and just in case you really want to abbreviate things, therefore has a mathematical symbol. 3 dots, like this. That means therefore. Therefore, opposite angles of a parallelogram are congruent. Okay, as I look through this, I'm thinking maybe I left out a step. And the step I really sort of left out, but I'm not going to put it in, is where I would go one more step and say angle A is congruent to angle C. And that's the definition of congruency. It means they're equal in measure. So like one more step down here that you don't have to write. But if I did, I'd say angle A is congruent to angle C, and angle B is congruent to angle D, which is kind of a repeat of this. It's just taking out the M in the front, which is the measure of this. And so they are congruent. That's just the definition of congruency. But it takes us to this big idea, which we did just prove. There's your first proof.